Wichita Falls, Texas went through the worst drought in its history in 2011 and 12. For 2 years in a row, the area saw its average annual rainfall roughly cut in half, decimating the levels in the 3 reservoirs used for the city's water supply. Looking ahead, the city realized that if the hot, dry weather continued, they would be completely out of water by 2015. 3 years sounds like a long runway, but when it comes to major public infrastructure projects, it might as well be overnight. Between permitting, funding, design, and construction, 3 years barely gets you to the starting line, so the city started looking for other options. And they realized there was one source of water nearby that was just being wasted. Millions of gallons per day just being flushed down the Wichita River. I'm sure you can guess where I'm going with this. It was the effluent from their sewage treatment plant. The city asked the state regulators if they could try something that had never been done before at such a scale. Take the discharge pipe from the wastewater treatment plant and run it directly into the purification plant that produces most of the city's drinking water. And the state said no. So they did some more research and testing and asked again. By then, the situation had become an emergency. This time, the state said yes, and what happened next would completely change the way cities think about water. I'm Grady, and this is Practical Engineering. You know what they say, wastewater happens. It wasn't that long ago that raw sewage was simply routed into rivers, streams, or the ocean to be carried away. Thankfully, environmental regulations put a stop to that, or at least significantly curbed the amount of wastewater being set loose without treatment. Wastewater plants across the world do a pretty good job of removing pollutants these days. In fact, I have a series of videos that go through some of the major processes if you want to dive deeper after this. In most places, the permits that allow these plants to discharge set strict limits on contaminants like organics, suspended solids, nutrients, and bacteria. And in most cases, they're individualized. The permit limits are based on where that effluent will go, how the water body is used, and how well it can tolerate added nutrients or pollutants. And here's where you start to see the issue with reusing that water. Clean enough is a sliding scale. Depending on how water is going to be used or what or who is going to interact with it, our standards for cleanliness vary. If you have a dog, you probably know this. They should drink clean water, but a few sips of a mud puddle in a dirty street, and they're usually just fine. For you, that might be a trip to the hospital. Natural systems can tolerate a pretty wide range of water quality, but when it comes to drinking water for humans, it should be very clean. So the easiest way to recycle treated wastewater is to use it in ways that don't involve people. That idea's been around for a while. A lot of wastewater treatment plants apply effluent to land as a disposal method, avoiding the need for discharge to a natural water body. Water soaks into the ground, kind of like a giant septic system, but that comes with some challenges. It only works if you've got a lot of land with no public access and a way to keep the spray from drifting into neighboring properties. Easy at a small scale, but for larger plants, it just isn't practical engineering. Plus, the only benefits a utility gets from the effluent are some groundwater recharge and maybe a few hay harvests per season. So why not send the effluent to someone else who can actually put it to beneficial use? If only it were that simple. As soon as a utility starts supplying water to someone else, things get complicated because you lose a lot of control over how the effluent is used. Once it's out of your hands, so to speak, it's a lot harder to make sure it doesn't end up somewhere it shouldn't, like someone's mouth. So naturally, the permitting requirements become stricter. Treatment processes get more complicated and expensive. You need regular monitoring, sampling, and laboratory testing. In many places in the world, reclaimed water runs in purple pipes so that someone doesn't inadvertently connect to the lines thinking they're potable water. In many cases, you need an agreement in place with the end user, making sure that they're putting up signs, fences, and other means of keeping people from drinking the water. And then you need a plan for emergencies. What to do if a pipe breaks, if the effluent quality falls below the standards, or if a cross connection is made accidentally. It's a lot of work, time, effort, and cost to do it safely and follow the rules, and those costs have to be weighed against the savings that reusing water creates. In places that get a lot of rain or snow, it's usually not worth it. But in many US states, particularly those in the Southwest, this is a major strategy to reduce the demand on fresh water supplies. Think about all the things we use water for where its cleanliness isn't that important. Irrigation is a big one, crops, pastures, parks, highway landscaping, cemeteries, but that's not all. Power plants use huge amounts of water for cooling, street sweeping, dust control. In nearly the entire developed world, we use drinking quality water to flush toilets. You can see there might be cases where it makes good sense to reclaim water, and despite all the extra challenges, its use is fairly widespread. One of the first plants was built in 1926 at Grand Canyon Village, which supplied reclaimed water to a power plant and for use in steam locomotives. Today, these systems can be massive, with miles and miles of purple pipes run entirely separate from the freshwater piping. I've talked about this a bit on the channel before. I used to live near a pair of water towers in San Antonio that were at 2 different heights above ground. That just didn't make any sense until I realized they weren't connected. One of them was for the reclaimed water system that didn't need as much pressure in the lines. Places like Phoenix, Austin, San Antonio, Orange County, Irvine, and Tampa all have major water reclamation programs. And it's not just a US thing. Abu Dhabi, Beijing, and Tel Aviv all have infrastructure to make beneficial use of treated municipal wastewater, just to name a few. Because of the extra treatment and requirements, many places put reclaimed water in categories based on how it gets used. The higher the risk of human contact, the tighter the pollutant limits get. For example, if a utility is just selling effluent to farmers, ranchers, or for use in construction, exposure to the public is minimal. Disinfecting the effluent with UV or chlorine may be enough to meet requirements. And often that's something that can be added pretty simply to an existing plant. But many reclaimed water users are things like golf courses, schoolyards, sports fields, and industrial cooling towers where people are more likely to be exposed. In those cases, you often need a sewage plant specifically designed for the purpose, or at least major upgrades to include what the pros call tertiary treatment processes, ways to target pollutants we usually don't worry about and improve the removal rates of the ones we do. These can include filters to remove suspended solids, chemicals that bind to nutrients, and stronger disinfection to more effectively kill pathogens. This creates a conundrum, though. In many cases, we treat wastewater effluent to higher standards than we normally would in order to reclaim it, but only for non-potable uses with strict regulations about human contact. But if it's not being reclaimed, the quality standards are lower and we send it downstream. If you know how rivers work, you probably see the inconsistency here, because in many places, down the river is the next city with its water purification plant whose intakes, in effect, reclaim that treated sewage from the people upstream. This isn't theoretical, it's just the reality of how humans interact with the water cycle. We've struggled with the problems it causes for ages. In 1906, Missouri sued Illinois in the Supreme Court when Chicago reversed their river, redirecting its water and all the city's sewage toward the Mississippi River. If you live in Houston, I hate to break it to you, but a big portion of your drinking water comes from the flushes and showers in Dallas. There have been times when wastewater effluent makes up half of the flow in the Trinity River. But the question is, if they can do it, why can't we? If our wastewater effluent is already being reused by the city downstream to purify into drinking water, why can't we just keep the effluent for ourselves and do the same thing? And the answer again is complicated. It starts with what's called an environmental buffer. Natural systems offer time to detect failures, dilute contaminants, and even clean the water a bit. Sunlight disinfects, bacteria consume organic matter. That's the big difference in one city, in effect, reclaiming water from another upstream. There's nature in between. So a lot of water reclamation systems, called indirect potable reuse, do the same thing. You discharge the effluent into a river, lake, or aquifer, then pull it out again later for purification into drinking water. By then, it's been diluted and treated somewhat by the natural systems. Direct potable reuse projects skip the buffer and pipe straight from one treatment plant to the next. There's no margin for error provided by the environmental buffer, so you have to engineer those same protections into the system. Real-time monitoring, alarms, automatic shutdowns, and redundant treatment processes. Then there's the issue of contaminants of emerging concern. Pharmaceuticals, PFAS, personal care products, things that pass through people or households and end up in wastewater in tiny amounts. Individually, they're in parts per billion or trillion, but when you close the loop and reuse water over and over, those trace compounds can accumulate. Many of these aren't regulated because they've never reached concentrations high enough to cause concern, or there just isn't enough knowledge about their effects yet. That's slowly changing, and it presents a big challenge for reuse projects. They can be dealt with at the source by regulating consumer products, encouraging proper disposal of pharmaceuticals instead of flushing them, and imposing pre-treatment requirements for industries. It can also happen at the treatment plant with advanced technologies like reverse osmosis, activated carbon, advanced oxidation, and bioreactors that break down microcontaminants. Either way, it adds cost and complexity to a reuse program, but really, the biggest problem with wastewater reuse isn't technical, it's psychological. The so-called yuck factor is real. People don't want to drink sewage. Indirect reuse projects have a big benefit here. With some nature in between, it's not just treated wastewater, it's a natural source of water with treated wastewater in it. It's kind of a story we tell ourselves, but we lose the benefit of that with direct reuse. Knowing your water came from a toilet, even if it's been purified beyond drinking water standards, makes people uneasy. You might not think about it, but turning the tap on, putting that water in a glass, and taking a drink is an enormous act of trust. Most of us don't understand water treatment and how it happens at a city scale, so that trust that it's safe to drink largely comes from seeing other people do it and past experience of doing it over and over and not getting sick. The issue is that when you add one bit of knowledge to that relative void of understanding, this water came directly from sewage, it throws that trust off balance. It forces you not to rely on past experience, but on the people and processes in place, most of which you don't understand deeply, and generally none of which you can actually see. It's not as simple as just revulsion. It shakes up your entire belief system, and there's no engineering fix for that. Especially for direct potable reuse, public trust is critical. So on top of the infrastructure, these programs also involve major public awareness campaigns. Utilities have to put themselves out there, gather feedback, respond to questions, be empathetic to a community's values, and try to help people understand how we ensure water quality no matter what the source is. But also, like I said, a lot of that trust comes from past experience. Not everyone can be an environmental engineer or licensed treatment plant operator, and let's be honest, utilities can't reach everyone. How many public meetings about water treatment have you ever attended? So in many places, that trust is just going to have to be built by doing it right, doing it well, and doing it for a long time. But someone has to be first. In the US, at least on the city scale, that drinking water guinea pig was Wichita Falls. They launched a massive outreach campaign, invited experts for tours, and worked to build public support. But at the end of the day, they didn't really have a choice. The drought really was that severe. They spent nearly 4 years under intense water restrictions. Usage dropped to 1/3 of normal demand, but it still wasn't enough. So, in collaboration with state regulators, they designed an emergency direct potable reuse system. They literally helped write the rules as they went, since no one had ever done it before. After 2 months of testing and verification, they turned on the system in July 2014. It made national headlines. The project ran for exactly 1 year. Then, in 2015, a massive flood ended the drought and filled the reservoirs in just 3 weeks. The emergency system was always meant to be temporary. Water essentially went through 3 treatment plants: the wastewater plant, a reverse osmosis plant, and then the regular water purification plant. That's a lot of treatment, which is a lot of expense, but they needed to have the failsafe and redundancy to get the state on board with the project. The pipe connecting the two plants was above ground and later repurposed for the city's indirect potable reuse system, which is still in use today. In the end, they reclaimed nearly 2 billion gallons of wastewater as drinking water, and they did it with 100% compliance with the standards. But more importantly, they showed that it could be done, essentially unlocking a new branch on the skill tree of engineering that other cities can emulate and build on. When I was studying in college, I think environmental engineering was one of the toughest subjects I took. But it's a field where you really get to be a jack of all trades, combining chemistry, biology, public health, and hydraulics into solutions that meet fundamental human needs. And you know what underlies all of it? It's math. What I learned throughout my career as an engineer was that mathematics isn't important for what it lets you accomplish, it's important for what it lets you understand. Grasping the underlying math opens the door to an entire world of practical tools, and today's sponsor, Brilliant, makes bridging that gap effortless. Brilliant's been sponsoring practical engineering videos for 7 years now. It's the longest partnership I've had, and I think the biggest reason for that is people watching this channel just keep finding value in learning new things in this interactive way. That, and they keep adding new lessons every month. The math courses go from the basics all the way through calculus, linear algebra, and beyond. I love learning. I think one of the most important things you can do in life is to always be broadening your horizons. We learn best not by reading or hearing, but by doing, and that's why I love Brilliant. The lessons just stick better when you're actually using the information while you learn. And learning a little bit every day creates a habit that pays off in the long run. You can try this completely free for 30 days and see if it's something that can help you get ahead in your career, get better at a hobby, or just enjoy the process of learning something new. If you love it, you'll get 20% off a premium subscription. Go to brilliant.org/practicalengineering, scan the code, or just click the link in the description below. I really like their website and their app, and I think you will too. Thank you for watching, and let me know what you think.